The sun rises exactly as it always has, quiet, golden, familiar. Yet its light carries 10% more energy than it did before. At first, nothing seems broken. Then the oceans begin storing more heat. Polar ice retreats. Rainfall shifts. Forests struggle as carbon dioxide slowly disappears from the air, and high above the clouds, water molecules begin breaking apart, allowing hydrogen to escape into space. A brighter sun would not destroy Earth in a single flash. It would change the planet patiently. One feedback, one vanished ecosystem, and one escaping molecule at a time. Thank you for spending part of your day or night here. Share in the comments what time it is where you're listening, and which corner of the world is watching with you. If this quiet journey through science feels worth continuing, leave a like, subscribe, and share it with someone who enjoys the deeper mysteries of our planet. Now, let the brighter sunlight fall and watch Earth begin to change. At first, a sun that is 10% brighter does not appear to change its character. It still rises with the same familiar shape, follows the same path across the sky, and pours light across oceans, forests, deserts, and cities. Yet beneath that outward familiarity, Earth's energy balance has shifted. The planet receives more solar power at every latitude and during every season. The increase is not a momentary flare or a brief pulse. It is steady, global, and permanent. That difference matters because Earth's climate is built around a narrow exchange between incoming sunlight and outgoing heat. Sunlight enters, part of it reflects back into space, and the rest is absorbed by the surface, clouds, oceans, and atmosphere. Earth then releases energy outward as infrared radiation. For long periods, the climate remains stable only when those two flows nearly balance. A brighter sun disturbs that balance from the beginning. More energy arrives than the planet is prepared to return, so heat begins to accumulate. The first response is not instant catastrophe, but adjustment. Land warms during the day, oceans store more heat, and the lower atmosphere becomes slightly more energetic. Each part of the climate system reacts at a different speed. Bare rock and dry soil respond quickly. The deep ocean responds slowly, taking decades and centuries to absorb the full change. Ice sheets respond more slowly still, but once their retreat begins, the consequences persist for very long spans of time. The planet therefore enters a transitional state in which the extra brightness is already present, while the full warming has not yet arrived. This delay hides the scale of what has changed. 10% sounds modest, especially when compared with the enormous range of temperatures already found across Earth. But the average solar energy reaching the top of the atmosphere is the foundation beneath every wind, current, cloud, and ecosystem. Increasing that foundation by 1/10 is not a local weather event. It is a new planetary condition. Even before feedbacks begin, the equilibrium temperature of Earth rises. The exact amount depends on clouds, atmospheric composition, surface reflectivity, and the behavior of water vapor, but the direction is unavoidable. The surface must become warmer before it can radiate enough additional heat to space to match the stronger sunlight. That warming spreads unevenly. Tropical regions already receive intense sunlight, but they are also efficient at moving heat through towering clouds, heavy rainfall, and atmospheric circulation. Polar regions receive less sunlight overall, yet they're far more sensitive because snow and ice act as bright shields. When those shields shrink, darker ocean and land absorb energy that would once have been reflected. The same increase in solar brightness therefore produces very different outcomes in different places. The Arctic and Antarctic begin to lose some of their long stability. Mountain glaciers retreat. Seasonal snow melts earlier and returns later. Frozen ground softens over wider regions. Coastlines do not vanish at once, but the slow rise of the oceans begins to become part of the planet's new background. The oceans are central to everything that follows. They cover most of Earth and absorb much of the excess heat. At first, this moderates the warming of the atmosphere, making the change seem gentler than it truly is. Yet stored heat is not harmless. Warmer water expands, raising sea level even before major ice loss occurs. Surface layers become more stable and resist mixing with colder water below. Oxygen becomes less soluble in warm water, placing stress on marine environments. Evaporation also increases, moving more water from the sea into the air. That added moisture carries latent heat, fuels heavier rainfall, and begins to strengthen the greenhouse effect because water vapor itself absorbs infrared radiation. In this way, the first imbalance created by the brighter sun starts to recruit the atmosphere into amplifying it. The climate does not simply accept 10% more sunlight and settle into a proportionally warmer state. It responds through a network of feedbacks, some that accelerate change and others that resist it. Clouds may reflect more sunlight in certain regions, partially shielding the surface. In other places, high thin clouds may trap additional heat. Vegetation may expand where rainfall improves, or collapse where heat and drought cross biological limits. Dust from drying soils may brighten the atmosphere, while soot and wildfire smoke may darken snow and speed its melting. No single response controls the whole planet. Instead, Earth searches for a new balance through countless linked adjustments. The atmosphere begins to reorganize because temperature differences drive its circulation. Hadley cells, the broad tropical overturning patterns that help shape deserts and trade winds, may widen. Storm tracks shift toward new latitudes. Monsoon systems strengthen in some regions and fail in others. The boundaries between wet and dry climates move across continents. Areas that once depended on predictable snowmelt receive more winter rain and less stored ice. River flow becomes less reliable. Heat waves become not only hotter but longer, since warmer soils dry more quickly and dry land cannot cool itself as effectively through evaporation. Forests that survived within a stable range of temperature and moisture begin to face repeated stress. Some migrate slowly toward cooler ground or higher latitude. Others are trapped by mountains, coastlines, poor soils, or the speed of change. The biological response begins quietly, long before the planet resembles a different world. Species alter their seasonal timing. Insects emerge earlier. Flowers open before their pollinators arrive. Marine organisms move toward cooler waters. Coral reefs suffer more frequent bleaching as warm seas disrupt the partnership between corals and the algae that feed them. These changes do not happen everywhere at once, but they accumulate. The brightest warning is not a single disaster. It is the gradual loss of synchrony in systems that evolve together. The extra sunlight also affects the upper layers of the atmosphere. More water vapor rises from a warmer surface, though most of it still condenses and falls before reaching great heights. The stratosphere remains comparatively dry at first, but the boundary that separates ordinary warming from long-term water loss begins to draw closer. Earth is not yet entering a full moist greenhouse, but the climate is moving in that direction. This possibility matters because water in the upper atmosphere can be broken apart by ultraviolet radiation. Hydrogen, being extremely light, can then escape into space. The process is slow, yet once it becomes efficient, the loss is effectively permanent. A brighter sun therefore changes more than temperature. It alters the long future of Earth's water. Still, the first stage is not the disappearance of oceans. It is the arrival of a warmer equilibrium that the modern biosphere has never known. Human societies, if they remain present, would experience the shift through coastlines, agriculture, water supply, disease ranges, migration, and infrastructure. Many low-latitude regions would become difficult to inhabit during the hottest periods, especially where humidity limits the body's ability to cool. Food production might move toward cooler latitudes, but soils, sunlight, and seasonal darkness would not always support the same crops. Cities built for an older climate would require constant adaptation, yet the deeper transformation extends beyond civilization. Over centuries and millennia, the planet's familiar climate zones would redraw themselves. Temperate forests would move poleward. Subtropical dry belts would expand. Ice would withdraw from coastlines where it had persisted for ages. Some places would become more productive for a time, while others would cross thresholds from which recovery becomes unlikely. This is the quiet force of a brighter star. It does not need to scorch the surface in a single instant. It changes the terms under which every part of the planet exchanges energy. This sun remains steady in the sky, but Earth no longer receives the amount of light around which its present oceans, ice sheets, atmosphere, and living systems have settled. The old balance begins to loosen, and the first signs of a different world appear not as one dramatic event, but as many small changes moving in the same direction. Nor does a 10% increase in sunlight mean that every thermometer rises by 10%. Temperature is not a direct percentage translation of incoming energy. The warmer surface emits more infrared radiation, and that outward flow eventually grows strong enough to oppose part of the added heating. The danger lies in everything that changes before a stable balance is restored, and in the possibility that feedbacks move the planet toward conditions far beyond the initial forcing. What begins as a simple change in stellar brightness becomes a test of clouds, ice, oceans, rocks, and life acting together. The first dawn under the brighter sun therefore contains the outline of every later transformation. The first consequence of a brighter sun is an energy surplus, but the deeper story begins with a long search for a new balance. Earth does not remain indefinitely in a state of uncontrolled warming simply because more sunlight arrives. As the surface grows hotter, it emits more infrared radiation into space. A warmer planet radiates more strongly than a cooler one, and this outward flow gradually rises until it can once again match the incoming solar energy. In the simplest possible world, this process would lead to a single new equilibrium temperature and then stop. Earth, however, is not a simple sphere of bare rock. It is wrapped in air, covered by oceans, marked by ice, dark forests, pale deserts, bright clouds, and living systems that alter the movement of energy. Every one of these features changes as the planet warms, and every change shifts the temperature at which balance can finally be restored. The new equilibrium is therefore not determined by sunlight alone. It is negotiated through the behavior of the entire climate system. The land reacts first. Dry ground has little capacity to store heat, so its temperature rises quickly when the energy supply increases. Regions already prone to heat extremes begin to experience longer and more persistent episodes of high temperature. Soil moisture becomes a crucial dividing line. Where water remains available, evaporation can carry heat away from the surface. Where soil dries, that cooling mechanism weakens, and almost all incoming energy goes directly into raising temperature. This is why some landscapes warm far more sharply than others. Oceans respond more slowly because water can absorb great amounts of heat without changing temperature as quickly as land. This thermal inertia acts like a delay built into the climate. The air may warm within years, while the deeper ocean takes centuries to reflect the full effect of the brighter star. During that delay, the planet appears to be approaching balance, Yet large reservoirs of cold water still wait below the surface. Heat continues to sink into them through mixing, currents, and the gradual movement of water masses. The climate therefore carries a hidden commitment to future warming. Even if the sun's brightness were held fixed from that moment onward, temperatures would continue to rise until the deep ocean had adjusted. The surface ocean also changes the atmosphere above it. Warmer water evaporates more readily, adding moisture to the air. Tropical regions hold far more water vapor because warm air can contain more before condensation begins. As a result, the strongest greenhouse amplification occurs where the atmosphere is already moist and energetic. Water vapor absorbs infrared radiation that would otherwise escape to space, so the planet must warm further before it can release enough energy to regain balance. This is one of the most important positive feedbacks in the climate system. It does not create the initial warming, but it magnifies it. A brighter sun provides the first push, and a moister atmosphere makes the final temperature higher than solar forcing alone would suggest. Clouds complicate the adjustment. Some clouds are low, thick, and bright. They reflect sunlight before it reaches the surface and can cool the planet. Others are high and thin. They allow much of the sunlight to pass through but slow the escape of infrared heat. As the planet heats, cloud cover, altitude, thickness, and distribution all change. Small differences in these responses can produce large differences in the final climate. A world with more reflective low clouds might resist part of the extra sunlight, while a world with more heat-trapping high clouds might move farther toward dangerous warming. Ice and snow introduce another major feedback. Their bright surfaces reflect a large fraction of incoming sunlight. As they retreat, darker ocean, rock, and soil are exposed. These darker surfaces absorb more energy, causing additional warming and further melting. The effect is especially powerful at high latitudes, where a small rise in average temperature can transform large areas from frozen to seasonally ice-free. Polar amplification emerges from this interaction. The poles warm faster than the global average, not because they receive the greatest increase in sunlight, but because they lose reflective cover, and because heat moves toward them through the atmosphere and oceans. The shrinking difference between equatorial and polar temperatures then alters large-scale circulation. Winds that once followed stable patterns begin to shift. Storm tracks migrate. Weather systems may slow, intensify, or appear in unfamiliar seasons as the planet searches for a new arrangement of heat transport. Warm air rises, cooler air sinks, and moving air carries energy from one region to another. A brighter sun strengthens some of these motions but weakens others by changing the contrast that drive them. Tropical circulation may expand toward higher latitudes. Dry subtropical zones may widen. Monsoon systems may carry more moisture because warmer air can hold more water. Yet their timing may become less reliable as land and sea heat at different rates. Heavy rainfall grows more intense in many places, while the intervals between storms may lengthen. The climate becomes capable of producing both stronger downpours and deeper droughts, two expressions of a faster water cycle. The oceans also redistribute the added energy. Surface currents carry tropical warmth toward cooler regions, while deep currents return colder water along slow global pathways. These currents depend on winds, temperature differences, and salinity. As polar ice melts and rainfall patterns change, fresh water enters regions where dense salty water once sank. This can weaken parts of the overturning circulation that ventilate the deep ocean and transport heat across hemispheres. Such changes do not stop the planet from warming, but they rearrange where that warming appears. Some regions may warm more slowly for a time if currents weaken, while others receive greater heat. Local cooling can therefore occur inside an overwhelmingly warming world. The search for equilibrium is uneven. full of pauses and regional reversals. Even though the global energy imbalance points in one direction, over long spans, the solid Earth begins to participate. Warmer temperatures and stronger rainfall in some regions accelerate the chemical weathering of silicate rocks. This process consumes carbon dioxide and eventually locks carbon into carbonate minerals. Because carbon dioxide is a greenhouse gas, its gradual removal can oppose part of the warming, yet the response is extremely slow. It unfolds over hundreds of thousands to millions of years, far longer than the immediate adjustment of air and land. The carbon cycle therefore behaves like a distant stabilizer rather than an emergency brake. It may reduce atmospheric carbon dioxide enough to moderate the final climate, but it can also create new problems for life by depriving plants of the gas required for photosynthesis. The planet can move closer to thermal balance while becoming less biologically generous. Balance, in this sense, does not mean safety. It only means that incoming and outgoing energy have become equal again. A desert world can be in equilibrium. A nearly ice-free world can be in equilibrium. A planet with collapsing forests, oxygen-poor seas, and lethal humid heat can still obey the laws of energy balance perfectly. The climate system does not seek habitability. It seeks a state in which energy no longer accumulates. Every feedback, current, cloud layer, and chemical cycle helps determine what that state looks like. Under a sun that remains 10% brighter, the final balance is almost certainly much warmer than the modern one. But the journey toward it may take centuries or longer because of the deep ocean and the slow response of ice. During that journey, conditions do not change smoothly. Thresholds are crossed. An ice shelf can weaken for decades and then break apart quickly. A forest can endure repeated drought until one final dry season converts it to grassland. A current can decline gradually, and then reorganize once density differences become too small to sustain its old path. These shifts give the transition a stair-step quality, with long periods of strain followed by abrupt change. Once the system settles, familiar maps of climate no longer apply. Regions once defined as temperate may resemble modern subtropics. Tropical zones may become difficult for large animals during the most humid heat. Polar coastlines may remain open water through much of the year. Mountain climates may climb so high that no cooler refuge remains above them. Yet even this warmer equilibrium is not necessarily permanent. The carbon cycle continues to evolve. Ice continues to disappear. Ecosystems continue to alter the surface, and the oceans continue to exchange heat with the depths. The brighter sun has not produced one final moment of adjustment. It has moved Earth onto a new path, where every temporary balance becomes the starting point for another slower transformation. The planet radiates more heat to space, but only after becoming a world unlike the one that first received the extra light. The warmer Earth begins to change most clearly where ocean and air meet. Every sea, lake, river, wetland, and damp stretch of soil releases water into the atmosphere. But the rate of that release depends strongly on temperature. As sunlight grows more intense and the surface warms, evaporation accelerates. At first, the change appears ordinary, yet the atmosphere is beginning to alter its own ability to hold heat. Water vapor is not merely a passenger carried upward from the oceans. It is a greenhouse gas, and among the most powerful in Earth's atmosphere. It absorbs infrared radiation emitted by the warm surface, preventing some of that energy from escaping directly into space. The extra sunlight from the brighter sun creates the first warming, but the added water vapor deepens it. This is the beginning of a feedback, a process in which an initial change produces effects that strengthen the change itself. The warmer the surface becomes, the more water enters the air. The more water vapor the air contains, the more heat it traps. The more heat it traps, the warmer the surface becomes. The cycle does not continue without limit in its early stages, because other parts of the climate system push back. Clouds reflect sunlight, rain removes moisture, a warmer planet radiates more energy to space. Even so, the water vapor feedback raises the final temperature well above what the brighter sun would produce on a dry world. Its power comes from the close connection between temperature and the amount of moisture air can contain. Warm air does not actively pull water into itself, but it allows more vapor to remain before condensation begins. A small rise in temperature therefore permits a significant rise in atmospheric moisture, especially in the lower layers where most weather occurs. The increase is greatest over warm oceans, where water is abundant and evaporation never lacks a source. Tropical air masses become more humid. Winds carry that moisture toward continents and higher latitudes. When the air rises and cools, the vapor condenses into cloud droplets and ice crystals, releasing stored heat into the atmosphere. This released energy strengthens storms and helps lift air still higher. The water cycle becomes more vigorous, moving greater amounts of heat from the surface into the sky. In this way, evaporation does not simply add moisture, it changes the structure and motion of the atmosphere. Rainfall begins to arrive in heavier bursts because a wetter atmosphere can supply more water to each storm. At the same time, the stronger evaporation that feeds these storms dries land more quickly between them. The result is a climate capable of producing intense rain and severe drought in the same place during different seasons. Wet periods become wetter, while dry periods can grow harsher. Rivers rise rapidly after storms and then fall more sharply. Soils lose moisture faster beneath hotter air. Plants close the small openings in their leaves to reduce water loss, but this also slows the intake of carbon dioxide needed for growth. Forests that once moderated their own climate through transpiration begin to struggle. Transpiration is the release of water vapor through leaves, a process that cools vegetation and helps form clouds. When heat and drought force plants to conserve water, that cooling weakens, allowing the land to warm further. Water vapor therefore links oceans, atmosphere, and living landscapes in a chain of responses that reaches far beyond temperature alone. Clouds sit at the uncertain center of this chain. When water vapor condenses, clouds can either resist warming or amplify it, depending on their altitude, thickness, and location. Low clouds are often bright and reflective. They send a substantial portion of sunlight back into space before it reaches the surface. If a warmer climate produces more low cloud cover over certain oceans, part of the sun's additional brightness may be offset. High clouds behave differently. They are cold at their upper surfaces and release relatively little infrared radiation to space, because they still allow much of the incoming sunlight to pass through. They can trap more heat than they reflect. A shift toward more high, thin clouds can therefore strengthen warming. The balance between these effects becomes one of the largest uncertainties in the planet's response. Their behavior depends on atmospheric circulation, airborne particles, ocean temperatures, and the height at which rising air becomes saturated. As the surface warms, that height often moves upward. Storm clouds grow taller. Their tops enter colder regions of the atmosphere. More heat is released through condensation as moist air climbs. Tropical thunderstorms become capable of transporting water farther above the surface than before. Most of that water still freezes, condenses, and falls back down. The upper atmosphere remains much drier than the layers below. This dryness is one of the barriers protecting Earth's oceans from rapid loss to space. Water that stays low returns through rain. Water that reaches the stratosphere faces a different fate. There, ultraviolet radiation can split water molecules apart. Oxygen may remain or enter other chemical reactions, while the much lighter hydrogen can drift upward and escape Earth's gravity. Under present conditions, this loss is slow. Colder layer near the top of the troposphere acts as a trap, causing rising water vapor to condense before it enters the stratosphere. As the surface becomes hotter and the atmosphere more humid, however, this cold trap becomes less effective. More water begins to leak past it. The brighter sun also supplies stronger radiation to break those molecules apart. Earth does not suddenly lose its oceans, but the pathway to permanent loss opens wider, before that threshold is fully crossed. Water vapor reshapes the lower atmosphere in quieter ways. Nights warm especially strongly because moisture slows the escape of heat after sunset. Regions that once cooled enough for plants, animals, and people to recover from daytime heat remain warm through the darkness. Humid heat becomes more dangerous than dry heat because evaporation from skin becomes less effective when the surrounding air is already close to saturation. Biological stress rises even where measured air temperature remains below the most extreme desert values. Large mammals find it harder to shed metabolic heat. Crops suffer when warm nights accelerate respiration, causing them to consume more of the energy they stored during the day. Insects expand into regions where cold once limited them. Fungi and plant diseases thrive in warm, damp conditions. The atmosphere's added moisture therefore becomes both a physical and biological force. It carries energy, alters weather, and changes the boundaries within which organisms can survive. The oceans also begin losing more fresh water to the air from regions of strong evaporation, increasing surface salinity in some places. Elsewhere, heavier rainfall and melting ice freshen the sea. These contrasts affect density and can modify currents that depend on the sinking of cold, salty water. A process beginning as invisible vapor above warm seas can eventually influence the slow circulation of the global ocean. The planet's heat engine becomes more active, but not more orderly. Energy moves faster through evaporation, condensation, winds, and storms, while familiar climate patterns become less reliable. There is a deceptive quality to water vapor because it leaves no permanent dark layer in the sky. It is transparent in visible light, and much of it cycles through the atmosphere in days rather than centuries. Yet the total amount present at any moment is controlled by temperature, and that makes it a powerful amplifier of whatever first caused the warming. Unlike carbon dioxide, which can accumulate because of emissions and remain for long periods, water vapor usually responds to the climate rather than leading it. The brighter sun warms the planet, and the atmosphere answers by holding more moisture. That answer then increases the warming. If Earth eventually reaches a stable state, the water vapor content will settle at a higher level than before, sustaining a hotter climate even after the fastest adjustments have ended. But if the warming pushes the atmosphere near a moist greenhouse, the feedback changes character. It no longer concerns only surface temperature and rainfall. It begins to threaten the long survival of the oceans themselves. The transition is not marked by a single visible line. It emerges as the upper atmosphere grows wetter, hydrogen escape accelerates, and the planet slowly gives away water that cannot return. A 10% brighter sun therefore turns the water cycle into something larger than a cycle. More water rises, falls, flows, and rises again. But a small fraction begins to leave the loop entirely. The process is gentle from one day to the next, almost impossible to witness directly. Yet across immense spans it can transform a blue planet into a drier and more fragile world. Water vapor first appears as the atmosphere's response to warmth. In time, it becomes the mechanism that carries Earth toward an unfamiliar threshold. The first visible sign of a planet absorbing more sunlight appears in places built from brightness itself. Snowfields, glaciers, sea ice, and frozen ground reflect much of the solar energy that reaches them. Their pale surfaces act as shields, returning light to space before it can become heat. When the sun grows 10% brighter, these shields receive more energy, and the balance that once preserved them begins to fail. Melting starts earlier in spring. Freezing arrives later in autumn. Summer ice grows thinner, and winter snow does not always rebuild what the warmer months remove. At first, the changes seem seasonal, but each shortened winter leaves the next one with less material to restore. Ice loses thickness, snow loses depth, and exposed surfaces remain dark for longer periods. This darkness matters because open ocean, bare rock, wet soil, and vegetation absorb far more sunlight than ice. The planet, therefore, does not merely lose frozen water. It changes the colour of its surface, and that colour change alters the flow of energy. More absorption produces more warming produces more melting. The feedback is simple in principle, yet immense in consequence. It is known as the ice albedo feedback, with albedo meaning the fraction of incoming light a surface reflects. Fresh snow has a high albedo, dark seawater has a low one. Replacing one with the other turns a reflective region into a solar collector. The effect is strongest near the poles, where large areas shift between frozen and exposed states. A brighter sun therefore produces polar amplification, a pattern in which high latitudes warm faster than the global average. The poles are not receiving the greatest amount of sunlight overall, but they are losing surfaces that once protected them from it. In the Arctic, sea ice begins to retreat from coastlines and shallow seas. Because this ice already floats, its melting does not directly raise sea level by much. Just as melting ice in a glass does not greatly change the water level, its climatic influence is far larger. Open water absorbs summer sunlight and stores heat. When autumn arrives, that stored heat escapes into the colder air, delaying the return of ice. The next winter begins later. The ice grows for less time, and the following summer starts with a thinner cover. This creates a memory within the ocean. One warm season prepares the conditions for another. The oldest, thicker sea ice disappears first from broad regions, replaced by younger ice that breaks more easily and melts more quickly. Waves travel farther across open water, striking the edges of the remaining ice and fracturing it. Winds move loose floes into warmer currents. The Arctic becomes less like a continuous frozen cap and more like a shifting mosaic of water and fragile ice. The transformation affects the atmosphere above it. A cold, ice-covered ocean transfers relatively little heat and moisture into the air. An open ocean releases both. Clouds form in new places. Snowfall patterns change. Warmer air spreads over nearby land, where frozen soils begin to thaw more deeply each summer. Permafrost, ground that remains frozen across many years, contains ancient organic matter preserved in cold conditions. As thaw reaches deeper layers, microbes begin breaking that material down, releasing carbon dioxide and methane. These gases add further greenhouse warming, linking the loss of surface ice to changes beneath the soil. The thaw also weakens the ground itself. Roads bend, buildings tilt, coastlines collapse, and lakes drain as once solid ice within the soil disappears. None of these processes requires the entire Arctic to become ice-free. They begin as soon as seasonal warmth lasts long enough to disturb the old frozen structure. Greenland responds differently because its ice rests on land. The ice sheet stores enough frozen water to reshape coastlines far beyond the island if a large fraction is lost. A brighter sun increases melting at the surface, especially around the lower edges where darker rock, dust, and meltwater absorb additional heat. Streams cut through the ice during summer, carrying water into cracks and down toward the bed. This water can lubricate the contact between ice and rock, allowing glaciers to move more quickly toward the sea. At the coast, warmer ocean water attacks floating glacier tongues from below. When those supports weaken, inland ice can accelerate. The loss is not uniform. High central regions may still receive snowfall, and warmer air can carry more moisture, but increased snowfall does not necessarily compensate for stronger melting and faster flow at the margins. As the bright surface lowers, it enters warmer air, making further melting easier. This elevation feedback adds another layer of instability. A thick ice sheet rises into cold atmospheric levels. A thinner one sits lower, where temperatures are higher. Once substantial thinning begins, the surface itself moves into conditions that favour continued loss. Across the planet, mountain glaciers experience a similar retreat. They are smaller than polar ice sheets, but their local importance is enormous. Many rivers depend on seasonal meltwater stored in high snow and ice. Under a brighter sun, glaciers release more water at first, swelling rivers and increasing flood risk. This temporary abundance can conceal the deeper decline. As the glaciers shrink, the stored reserve diminishes. Eventually, the seasonal melt arrives earlier and ends sooner, leaving less water during warm, dry months. Valleys that depended on a slow summer release face unstable supplies. Dark dust, wildfire ash, and soot settle on snow, lowering its reflectivity and hastening melt. Exposed rock warms and transfers heat to the ice at its edges. Small glaciers vanish entirely, leaving behind bare basins, unstable slopes, and new lakes held by loose sediment. In Antarctica, the response is divided by geography. The vast interior remains extremely cold for a long time, but coastal regions and ice shelves become increasingly vulnerable. Floating ice shelves do not add much to sea level when they melt, yet they act as braces that slow the movement of land ice behind them. Warmer air melts their surfaces, while warmer currents thin them from below. Meltwater collects in ponds and forces open fractures, sometimes breaking large shelves apart. Once that support disappears, glaciers feeding the shelf can speed toward the ocean. West Antarctica is especially sensitive because much of its bed lies below sea level. Warm seawater can reach beneath the ice and move the grounding line, the place where the glacier leaves the bed and begins to float, farther inland. In some regions, the bed slopes downward away from the coast. Retreat there can become self-sustaining, because thicker ice is exposed to the ocean as the grounding line moves inland, increasing the flow and making further retreat easier. The result is not an instant collapse, but a process that may continue for centuries even if the climate later stabilizes. This is one reason ice sheets are dangerous markers of planetary change. They respond slowly, yet once committed to retreat, they may be difficult to stop. The loss of ice also reshapes circulation. Fresh meltwater spreads across polar seas, making surface water less salty and less dense. This can interfere with the sinking of cold water that helps drive deep ocean currents. Changes in sea ice alter where the ocean exchanges heat, moisture, and gases with the atmosphere. The contrast between warm lower latitudes and cold poles weakens, modifying wind patterns that depend on that difference. Weather far from the ice may begin to change because the poles no longer anchor the climate in the same way. Storm tracks shift. Persistent pressure patterns appear in unfamiliar places. The exact regional outcomes remain complex, but the direction of the polar transformation is clear. Brighter sunlight strips away reflective cover and replaces it with surfaces that welcome more heat. The planet becomes darker in the places where darkness matters most. Even seasonal snow contributes to this widening change. Spring snow retreats northward and uphill, exposing soil earlier in the year. Forests absorb sunlight that snow-covered ground once reflected. Earlier warmth dries vegetation and lengthens fire seasons. Smoke and ash then darken remaining snowfields, feeding back into faster melt. The boundary between frozen and unfrozen land moves across landscapes that have held it for thousands of years. Species adapted to sea ice, snow cover, and cold seasonal timing lose habitat faster than migration can replace it. Coastal communities face erosion as sea ice no longer protects shorelines from waves. The physical and biological worlds shift together. A 10% brighter sun therefore does more than raise average temperature. It removes a planetary mirror. Each vanished snowfield and each widening stretch of open polar water allows the Earth to retain a little more of the star's energy. The warming that began in the sky becomes written into the surface, and the surface sends that warming back into the atmosphere. Ice retreats. Darkness expands, and the poles begin to reveal how a small change in brightness can become a much larger change in climate. As the planet warms beneath a brighter sun, weather does not simply become a hotter version of what came before. The atmosphere begins to reorganize because every wind, storm track, monsoon, and season depends on differences in temperature. Warm air rises, cooler air sinks, and the movement between them carries heat from one region to another. When the sun supplies 10% more energy, those contrasts shift across oceans and continents. Some strengthen, others weaken, and the familiar paths of weather begin to drift. The result is not a single global pattern, but a slow redrawing of the climate's moving architecture. In the tropics, intense sunlight drives air upward in broad belts of convection. Moisture condenses into towering clouds, releasing heat and feeding circulation high above the surface. The rising air then spreads toward higher latitudes, cools, and sinks in the subtropics, creating many of the world's great desert zones. This vast overturning system is known as the Hadley circulation. Under stronger solar heating, its edges are likely to move poleward. The subtropical dry belts expand, carrying arid conditions into regions that once stood at the margins of dependable rainfall. Mediterranean climates become hotter and drier. Grasslands face longer dry seasons. Forests near the edges of the tropics lose moisture and become more vulnerable to fire. Areas that still receive heavy rain may experience it in shorter, more violent bursts, while neighbouring regions spend longer periods beneath clear, drying skies. The movement of these circulation cells also changes the paths followed by storms. In the middle latitudes, weather is guided by strong ribbons of high-altitude wind known as jet streams. These winds form partly because of the contrast between warm tropical air and cold polar air. As the poles warm faster than lower latitudes, that contrast weakens near the surface, while changes higher in the atmosphere complicate the response. Jet streams may shift toward the poles, alter their speed, or develop larger bends that allow weather systems to linger. A slow-moving ridge of high pressure can hold heat over a continent for days or weeks. A deep trough can draw cold air far south even within a warmer world. The average temperature rises, but the path toward that average is uneven. Persistent patterns become more important than isolated extremes because they give heat, rain, or drought time to accumulate. A single hot day strains crops and cities. A stationary heat dome lasting many days dries soils, raises nighttime temperatures, and pushes living systems closer to their limits. The brighter sun also strengthens the water cycle. Warmer seas release more vapor, and warmer air can carry more moisture before condensation begins. When storms form, they therefore have access to a larger reservoir of water. Rainfall becomes heavier where rising air is already favored. Tropical storms, monsoon systems, and frontal storms can release more rain in shorter periods. Floods become more destructive even in places where total annual rainfall changes only slightly. Rivers that once rose gradually may surge with little warning. Mountain slopes fail under saturated soil. Cities designed around older drainage patterns struggle to move the water away. Yet stronger rainfall does not mean a uniformly wetter planet. Evaporation also accelerates, and many regions lose moisture faster than rain can replace it. The same atmosphere can produce deeper drought between more intense storms. This contrast becomes one of the defining features of the changed climate. Water moves through the system faster, but it is not distributed more evenly. Monsoons become especially sensitive because they depend on the seasonal contrast between land and ocean. Land heats quickly under the brighter sun, while the ocean responds more slowly. In some regions, this sharper contrast strengthens the pull of moist air onto the continent, producing heavier summer rains. In others, changing sea temperatures, altered winds, or persistent high pressure disrupt the timing of the monsoon. The rain may arrive late, withdraw early, or fall in a few destructive episodes rather than a long nourishing season. Agriculture built around reliable seasonal rhythms becomes increasingly fragile. Seeds may be planted before the rains fail. Crops may survive early growth only to face extreme heat during flowering. Reservoirs may fill rapidly and then decline through months of intense evaporation. A monsoon does not need to vanish to become dangerous. It only needs to become less predictable. Over the oceans, the warmer surface changes tropical cyclones. These storms draw energy from warm water and release it through condensation in rising air. A brighter sun expands the regions where ocean temperatures can support powerful storms and lengthens the portion of the year when those conditions persist. Not every storm becomes stronger, because cyclone formation also depends on wind shear, atmospheric stability, and the presence of an initial disturbance. Yet the storms that do organize can carry more moisture and may reach greater intensity when other conditions allow. Their rainfall spreads over wider areas. Storm surge rises on top of a higher sea level. Slow movement near coastlines prolongs wind and flooding. Places once near the edge of cyclone zones may encounter them more often, as warm water reaches farther from the tropics. The geography of risk moves with the climate. Ocean patterns that influence weather from year to year also shift. Large exchanges of heat between the tropical Pacific and the atmosphere can alter rainfall across much of the world. Under a brighter sun, the background ocean becomes warmer. But the difference between warm and cool regions may change in ways that affect these cycles. Some phases may grow more intense, while others may become less regular. Similar changes occur in the Atlantic and Indian Oceans, where surface temperatures guide monsoons, droughts, and storm tracks. The climate's natural variability does not disappear. It operates on top of a warmer baseline, meaning that an unusually hot or dry year begins from conditions already closer to dangerous thresholds. Extremes that were once rare become easier to reach, and combinations of hazards become more common. Heat can arrive during drought. Heavy rain can follow wildfire, sending mud across burned slopes. A storm surge can coincide with river flooding. The damage comes not only from stronger individual events, but from the way altered patterns allow them to overlap. Seasons also lose some of their old boundaries. Spring warmth arrives earlier in many regions, triggering snowmelt, plant growth, and insect emergence. Autumn cold arrives later, extending warm conditions but also lengthening periods of drought, wildfire, and biological activity. Winter becomes shorter and less stable in middle latitudes. Cold outbreaks still occur when atmospheric patterns pull polar air southward, but they unfold against a warmer background and are interrupted more often by rain or thaw. Snow cover becomes less dependable, changing soil moisture and river flow months later. Plants and animals respond to temperature, daylight, rainfall, and food availability. But these signals no longer shift together. A tree may leaf out early during unusual warmth, only to be damaged by a later frost. Birds may migrate according to daylight, while insects emerge according to temperature. Predators, prey, pollinators, and flowering plants fall out of step. Weather patterns become biological patterns because timing is one of the foundations of ecosystems. Fire becomes another expression of the reorganized climate. Hotter air draws moisture from vegetation, and longer dry seasons create larger regions of flammable material. Lightning may increase in some storm environments, while shifting rainfall encourages rapid plant growth followed by severe drying. Forests that once burned occasionally may face repeated fires before mature trees can return. Smoke darkens the sky, alters cloud formation, and travels across continents. In high latitudes, soot settles on snow and ice, lowering their reflectivity and accelerating melt. Fire therefore links weather, ecosystems, atmospheric chemistry, and the loss of frozen surfaces. It can convert forests from carbon stores into sources of greenhouse gases, adding another feedback to the warming. Despite these disruptions, the atmosphere continues trying to transport heat away from regions of surplus. Winds strengthen where temperature and pressure contrasts sharpen. They weaken where those contrasts fade. Storms carry energy upward and toward the poles. Ocean evaporation cools the surface even as the resulting vapor traps more heat elsewhere. The climate system remains active, adaptive, and physically ordered. But its order no longer matches the patterns around which modern ecosystems and civilizations developed. The danger lies less in weather becoming chaotic than in weather becoming unfamiliar. Old averages lose their usefulness. Coastlines, farms, reservoirs, forests, and cities remain fixed while the zones of heat, rain, wind, and storm move around them. A 10% brighter sun therefore changes the atmosphere as though the planet's invisible machinery has been reset. The winds still blow, clouds still gather, and seasons still turn, but their timing and reach begin to drift. What once seemed permanent becomes only a temporary arrangement, and the warmer sky starts writing a new climate across the surface below. As Earth warms beneath a sun that remains 10% brighter, the atmosphere begins to lose carbon dioxide through one of the slowest stabilizing processes on the planet. The change does not arrive through a sudden collapse or a single chemical event. It begins wherever rainwater meets exposed rock. Carbon dioxide dissolves into droplets, forming a weak acid that reacts with silicate minerals in mountains, soils, riverbeds, and fresh volcanic surfaces. The weathered material is carried toward the oceans, where dissolved carbon eventually becomes part of carbonate minerals and sediments. Over immense spans of time, some of that carbon is buried, removing it from the atmosphere. This process is part of the long carbon cycle, a planetary exchange among air, water, rock, and the deep interior. It acts so slowly that it cannot prevent rapid warming on human timescales. But under a brighter sun, it becomes increasingly important. Higher temperatures accelerate many chemical reactions. Stronger evaporation intensifies parts of the water cycle, while heavier rainfall in wet regions exposes minerals to more flowing water. Warmer soils support faster chemical breakdown where moisture remains available. Each of these changes increases the rate at which silicate weathering consumes atmospheric carbon dioxide. The planet begins to compensate for stronger sunlight by weakening one of its greenhouse blankets. This response resembles a thermostat, though it is neither precise nor designed. A warmer climate draws down more carbon dioxide, reducing heat retention. A cooler climate slows weathering, allowing volcanic emissions to rebuild atmospheric carbon dioxide over time. across geological ages. This feedback helps keep Earth within a range where liquid water can persist despite the gradual brightening of the sun. It does not hold temperature fixed, and it cannot protect every ecosystem. But it has prevented the climate from drifting as rapidly as stellar evolution alone might suggest. Under a sun suddenly brighter by a tenth, the same mechanism becomes a major force in the long adjustment. Volcanoes continue releasing carbon dioxide from the interior, but weathering begins removing it more quickly. If removal exceeds supply for long enough, the atmospheric concentration declines. The greenhouse effect weakens, partially opposing the added sunlight. Yet this apparent defense carries a hidden cost. Carbon dioxide is not only a heat-trapping gas, it is also a raw material for photosynthesis. Plants take in carbon dioxide and use sunlight to build sugars, releasing oxygen as a byproduct. As the atmosphere loses carbon, the climate may become somewhat less hot than it would otherwise be, but the biological foundation of the surface begins to starve. The contradiction is quiet and profound. A process that protects the planet from greater warming gradually makes the planet less suitable for the organisms that transformed its air. The decline does not affect all plants equally. Most trees, shrubs, and temperate crops use a form of photosynthesis known as the C3 pathway. This system works well under moderate temperatures and relatively abundant carbon dioxide, but it becomes inefficient when carbon levels fall and heat rises. The enzyme that captures carbon can also react with oxygen, producing a wasteful process called photorespiration. Warm conditions make this problem worse. As carbon dioxide becomes scarcer, plants must open tiny pores on their leaves more widely or for longer periods to gather enough of it. Those pores also release water vapor. In a hotter climate, the attempt to acquire carbon therefore increases water loss. Plants face two pressures at once. The air offers less carbon for growth, while the warmer atmosphere pulls more moisture from their leaves. Forests begin to grow more slowly even where rainfall remains adequate. In drier regions, the cost becomes severe. Trees close their pores to conserve water, but doing so limits carbon intake and reduces photosynthesis. Growth weakens, defenses against insects decline, and recovery from fire or drought becomes slower. Some species migrate toward cooler or wetter regions, but ecosystems cannot move as a single intact unit. Soil organisms, fungi, pollinators, seed dispersers, and competing plants all respond at different rates. The green world begins to fragment. Plants using the C4 pathway have an advantage because they concentrate carbon dioxide inside specialized cells before photosynthesis begins. This allows them to function more efficiently under high heat, strong light, and low carbon conditions. Many tropical grasses and some important crops use this method. As C3 plants retreat, C4 grasses may spread across regions once dominated by woodland. The change alters fire patterns because grasses grow quickly, dry rapidly, and can carry flames across broad landscapes. Repeated fire prevents young trees from returning, reinforcing the shift from forest to open grassland. For a time, the planet may remain visibly green, but its vegetation becomes simpler and more drought-tolerant. The loss of forest changes more than scenery. Trees move water from soil into the atmosphere, helping form clouds and recycle rainfall across continents. Their roots stabilize ground, their leaves shade soil, and their bodies store carbon. When forests thin, local rainfall can weaken, erosion can increase, and additional carbon can return to the air through decay and fire. These effects temporarily resist the long drawdown of carbon dioxide, but they do not halt it if rock weathering continues to outpace geological emissions. The balance shifts through competing processes. Warming accelerates weathering. Vegetation loss reduces biological carbon storage. Fires release carbon, oceans absorb some of it, Volcanoes supply more from below. The final atmospheric level emerges from the combined movement of carbon through all these reservoirs. Oceans play a central role because they hold far more carbon than the atmosphere. Carbon dioxide dissolves into seawater, where it enters a series of chemical reactions and becomes bicarbonate and carbonate ions. Marine organisms use some of this material to build shells and skeletons. When they die, part of it sinks toward the seafloor. Warmer water generally holds less dissolved gas, which can return carbon dioxide to the air, but the long weathering cycle continues delivering dissolved carbon from continents to the sea. Ocean chemistry changes as the atmosphere changes, affecting the availability of carbonate for shell-forming organisms. Rising temperature also reduces oxygen in seawater and strengthens layering between warm surface water and colder depths. Nutrients become harder to bring upward in some regions. Marine productivity shifts, and the biological pump that carries carbon into the deep ocean changes with it. The planet's response is therefore not a simple decline along a smooth curve. It is a long negotiation between chemistry, climate, geology, and life. Fresh volcanic rock can weather rapidly, especially in warm and wet conditions. Mountain building exposes new mineral surfaces. Rivers grind rock into smaller particles, increasing the area available for reaction. Plate tectonics changes rainfall patterns, coastlines, and the position of continents. A large dry continent may weather slowly despite high temperature, while a mountainous tropical region can remove carbon efficiently. As the brighter sun reshapes rainfall, it also reshapes the geography of carbon removal. Wet zones become powerful chemical sinks. Expanding deserts become less active because weathering requires liquid water. The global effect depends on where warmth and moisture overlap. This makes the long-term future uncertain in detail, but the central direction remains clear. Stronger sunlight pushes the climate toward greater weathering and lower atmospheric carbon dioxide. Eventually, the decline approaches biological thresholds. C3 plants become unable to maintain positive growth across much of the surface. Forest canopies thin, then fail to regenerate. Food webs built on leaves, wood, fruit, seeds, and nectar begin to lose their foundation. Herbivores decline first, followed by predators and scavengers. Soil ecosystems change as the supply of roots and fallen plant matter shrinks. Oxygen does not vanish immediately because the atmosphere contains a vast reservoir, but the process that replenishes it weakens. C4 plants and other specialized organisms persist longer, especially in warm open environments, yet they too depend on carbon dioxide. As levels continue falling and temperatures continue rising, even their advantage narrows. The brighter sun has forced Earth into a difficult trade. Keeping more carbon dioxide would intensify greenhouse warming and move the planet more quickly toward dangerous heat. Removing it slows that warming but undermines photosynthesis. The long carbon cycle protects liquid water by sacrificing biological richness. There is no intention in this exchange, only physical response. Rocks react faster in warmth. Carbon leaves the air. Plants struggle. The planet moves toward a new equilibrium that may be thermally stable and biologically impoverished. Across millions of years, mountains soften, rivers carry their dissolved remains to the sea, and sediments quietly store carbon beneath the ocean floor. The process is almost invisible from one lifetime to the next, yet it may determine how long complex life can endure under the brighter star. Earth's hidden defense is working. But the cost of that defense is beginning to spread through every leaf. The decline of plant life begins long before Earth becomes a barren world, under a sun that is 10% brighter. Vegetation first confronts a climate that is warmer, drier in many regions, and increasingly unstable. At the same time, The slow weathering of silicate rocks draws carbon dioxide from the atmosphere. These two pressures arrive from opposite directions but meet inside every leaf. Heat increases the demand for water and raises the cost of maintaining living tissue. Falling carbon dioxide reduces the raw material available for photosynthesis. A plant must therefore work harder to obtain less, while losing more water in the process. The first signs appear as slower growth, shorter growing seasons in hot regions, and greater damage during drought. Forests do not disappear at once. Their decline begins through repeated stress. A tree survives one dry year, then another, but each season leaves fewer reserves in its roots and wood. Insects and disease take advantage of weakened defences. Fire removes mature canopies. Seedlings fail to establish beneath hotter, drier conditions. Over time, the forest still appears present from a distance, yet its ability to replace itself is fading. Most trees use the C3 form of photosynthesis. In this pathway, an enzyme captures carbon dioxide from the air and begins the process of building sugars. The same enzyme can also react with oxygen, especially when temperatures rise and carbon dioxide becomes scarce. This competing reaction wastes energy and releases some of the carbon the plant has already captured. The result is photorespiration, a process that becomes increasingly costly in a hotter, low-carbon atmosphere. Plants respond by opening tiny pores called stomata on the surfaces of their leaves. Through these pores, carbon dioxide enters, but water vapor escapes. When carbon dioxide is abundant, a plant can gather what it needs while keeping those pores partly closed. When carbon dioxide declines, the pores must remain open longer. Under warmer conditions, this causes even greater water loss. The plant faces a choice with no safe outcome. Closing the pores conserves water but limits photosynthesis. Opening them allows carbon intake but risks dehydration. Heat sharpens this dilemma by increasing evaporation from both soil and leaf. Forests in humid regions withstand the pressure longer because rainfall remains high, but even they are vulnerable when dry seasons intensify. Tropical forests depend on the recycling of water through vegetation. Roots draw moisture from the ground, and leaves release it into the atmosphere, where it helps form clouds and rain. If enough trees die or stop transpiring, the region produces less of its own rainfall. The forest becomes drier, which causes further decline. A boundary can be crossed where tall, closed canopy forest gives way to open woodland or grassland. The transition may unfold unevenly, leaving islands of surviving trees along rivers, hillsides, and wetter soils. These fragments store less carbon, produce less moisture, and support fewer species. Animals that depend on fruit, leaves, bark, or canopy shelter lose their habitats. Pollinators and seed dispersers decline, making it even harder for the remaining plants to reproduce. Temperate forests also begin moving toward cooler latitudes and higher elevations. But migration is far slower than climate change. Individual trees cannot travel. Their ranges shift only as seeds establish beyond the old boundary and mature forests die behind it. Roads, farms, cities, mountains, and coastlines interrupt that movement. Suitable soils may not exist where the climate becomes favourable. New pests may arrive before the trees that resist them. Forest communities therefore do not move intact. They break apart and recombine, often losing the relationships that once held them together. Mountain forests face a narrowing refuge. As temperatures rise, species climb upward, but the available land shrinks near the summit. Eventually, there is nowhere colder to go. High elevation plants disappear first from the lowest parts of their range, then from isolated ridges, and finally from the last cool slopes. Grasslands appear more resilient because many grasses use the C4 pathway. which concentrates carbon dioxide inside their tissues and reduces photorespiration. This gives them an advantage in hot, bright, low-carbon environments. As trees and C3 plants decline, C4 grasses spread across open land. For a time, the planet may become more grassy rather than immediately less green. Yet this apparent success hides another transformation. Grasslands store less carbon above ground than forests. They burn more readily during dry seasons. Fire moves quickly through dead stems, killing young trees and maintaining open landscapes. Herbivores adapted to grazing may expand, but species dependent on forest decline. Soil erosion increases where intense rain falls on burned or sparsely covered ground. The surviving vegetation becomes dominated by plants that can grow quickly, tolerate heat, and recover after fire. Diversity narrows as specialized species lose the stable conditions they require. Agriculture, if it still exists, faces the same physical limits. Many major food crops use C3 photosynthesis and suffer when heat interferes with flowering, grain formation, and seed development. Warmer nights increase respiration, causing plants to consume more of the sugars produced during the day. Drought reduces leaf area and shortens growth. Heavy rain can wash nutrients from soil or destroy roots through flooding. Even crops using the C4 pathway cannot escape extreme heat or water loss. Their carbon concentrating system offers an advantage, not immunity. As atmospheric carbon dioxide continues to fall, all photosynthetic pathways eventually become constrained. Irrigation can delay the decline in some regions, but warmer conditions increase evaporation from reservoirs, canals, and fields. Soils lose organic matter more quickly as microbes become more active in warmth. Repeated cultivation and erosion reduce fertility. The landscape must supply more food under conditions that make biological production less reliable. Natural ecosystems begin to simplify in parallel. Leaves become smaller or tougher. Growth shifts toward brief periods after rain. Annual plants complete their life cycles quickly and survive dry years as seeds. Deep-rooted shrubs replace shallow-rooted species. Succulents and other water-storing plants expand where temperature remains tolerable. In coastal and river environments, wetlands retreat as evaporation rises and water flow becomes less dependable. Mangroves may move inland where terrain allows, but rising seas, heat, and changing salinity compress them against human structures or steep ground. Freshwater plants suffer when lakes shrink and rivers warm. Algae may bloom in nutrient-rich waters, yet these blooms often create oxygen-poor conditions when they decay. The weakening of land vegetation also affects atmospheric oxygen, though not immediately. Earth's air contains an immense reservoir built over geological time. The decline of photosynthesis does not remove that oxygen in a sudden fall. Instead, the long balance changes. Less oxygen is produced, while respiration, decay, weathering, and combustion continue consuming it. Across very long spans, oxygen levels begin to decline. Complex animals, with their high energy demands, become increasingly vulnerable as heat, habitat loss, and lower oxygen act together. Food webs contract from the base upward. Herbivores lose both quantity and quality of food. Predators decline as prey becomes scarce. Decomposers persist longer because dead material remains available, but even they depend on moisture and suitable chemistry. The biosphere does not fail through one universal extinction event. It thins in stages, with each loss making the remaining system less stable. Some plants survive in refuges where groundwater reaches the surface, where mountains create cooler air, or where clouds shield the land from direct sunlight. Others persist near high latitudes during favorable seasons. These refuges become increasingly isolated as surrounding regions turn hot, dry, or carbon poor. Evolution continues, favouring organisms that use water efficiently, tolerate heat, and capture carbon at very low concentrations. Yet evolution works with existing biology and requires generations, populations, and time. It cannot guarantee a solution to every physical limit. Photosynthesis depends on carbon dioxide, liquid water, and temperatures that preserve complex molecules. As those conditions narrow, so does the range of possible adaptation. The green world therefore retreats not because sunlight has become scarce, but because there is too much energy and too little usable carbon. The brighter sun fills the surface with light, while the atmosphere slowly deprives leaves of the gas needed to turn that light into life. Forests open, grasslands spread, fires lengthen, and food webs lose their foundation. Earth remains illuminated, perhaps more brilliantly than before, but its living surface becomes quieter. The paradox deepens with every age. The star provides more energy than ever, yet the planet becomes less able to use it. The oceans do not need to boil before Earth begins to lose them. Under a sun that is 10% brighter, the decisive change begins much earlier. While the surface still holds broad seas and rain continues to fall, the first warning is not a shoreline vanishing overnight, but a steady increase in the amount of water entering the atmosphere. Warmer oceans evaporate faster. Warmer air holds more vapor. Storms carry that moisture upward, and the upper boundary of the weather layer becomes less effective at keeping water confined near the surface. Earth begins moving toward a moist greenhouse, a climate state in which the lower atmosphere remains wet enough and warm enough for significant water vapor to reach the stratosphere. The phrase does not describe a planet wrapped in constant steam. It describes a change in altitude. Water that once condensed and returned as rain begins to pass into layers where it can be broken apart and lost. This makes the moist greenhouse different from ordinary global warming. A warmer climate can still maintain oceans if most water remains trapped in the lower atmosphere and continues cycling between sea, cloud, rain, ice, river, and ground. A moist greenhouse weakens that containment. It turns part of the water cycle into a one-way path towards space. The oceans remain visible for a very long time, but their security has changed. The process begins with evaporation. Tropical seas receive intense sunlight and become the main source of atmospheric moisture. Their surface layers warm, become more strongly separated from colder water below, and exchange heat with the air at an increasing rate. Winds lift vapor from the ocean and carry it into regions of rising air. There, the vapor condenses, releasing heat and powering deep clouds. Most of the water still falls back as rain, but the warmer atmosphere raises the level at which condensation occurs. Storm towers reach higher. The layer that normally freezes out most rising moisture becomes less efficient. This layer is sometimes called the cold trap because its low temperature causes water vapor to condense before it can enter the stratosphere. As the surface warms and the entire lower atmosphere becomes wetter, more vapor leaks through. Once water reaches the stratosphere, it remains exposed to ultraviolet radiation. The radiation splits water molecules into hydrogen and oxygen. Oxygen is heavy and reactive, but hydrogen is light enough to rise gradually toward the outer atmosphere. Some of it reaches speeds or altitudes from which it no longer returns. Each escaping atom represents an almost unimaginably small loss, yet the process continues across the whole planet and across immense spans of time. The sea does not drain through a visible opening, it thins through chemistry. The significance of a 10% brighter sun lies in how close that increase may place Earth to this threshold. Climate models differ because clouds, atmospheric circulation, surface reflectivity, and the distribution of water all influence the outcome. A planet covered by reflective clouds could resist warming more effectively than one dominated by heat-trapping cloud layers. Continents matter because dry land heats differently from ocean. Rotation rate, atmospheric pressure, and the abundance of other greenhouse gases also shape the final climate. There may not be one exact surface temperature at which a moist greenhouse begins everywhere. Instead, the transition can emerge region by region, first through especially warm and humid parts of the tropics, then across wider areas as the upper atmosphere grows wetter. The danger is not that the oceans reach their boiling point at sea level. Long before that, evaporation can become strong enough to supply a persistent upward flow of water. The greenhouse effect of water vapor adds to the problem, as more moisture fills the air. More outgoing infrared radiation is absorbed and re-emitted before it can escape to space. This raises the altitude from which Earth effectively radiates heat. Because higher air is colder, it emits energy less efficiently. The surface must warm further to restore balance. That additional warming drives more evaporation, increasing atmospheric moisture again. The feedback can intensify without immediately becoming a runaway greenhouse. In a full runaway state, the outgoing heat reaches a limit and added solar energy can no longer be balanced by greater radiation to space. Surface temperatures then rise dramatically until the oceans evaporate. A moist greenhouse is a slower and less extreme state, but it may still be fatal to the long-term survival of surface water. The planet can remain below a complete runaway while steadily losing hydrogen. This distinction makes the transformation quieter and more deceptive. Oceans still cover the continent's margins. Rain still falls. Rivers may still flow, yet the upper atmosphere is carrying away the future of the sea. As evaporation increases, the oceans also become more stratified. Their warm surface layers grow lighter and resist mixing with colder, denser water below. This reduces the upward supply of nutrients in many regions. Microscopic algae near the surface depend on nutrients brought from depth, so marine productivity begins to decline where mixing weakens. These organisms form the base of much of the oceanic food web and contribute a large share of Earth's photosynthesis. Their reduction affects fish, marine mammals, seabirds, and the movement of carbon into the deep sea. Warmer water also holds less dissolved oxygen. At the same time, stronger stratification prevents oxygen, rich surface water, from reaching deeper layers. Low oxygen zones expand, especially where decaying organic matter consumes what remains. Some marine organisms migrate toward cooler waters or shallower oxygenated regions. Others become trapped between overheated surface layers and suffocating depths. Coral reefs decline early because they are sensitive to sustained heat, acidification, and changes in light and chemistry. The oceans remain vast, but their living structure becomes thinner. Sea level continues to rise as warm water expands and land ice melts. Coastal plains are flooded, estuaries shift inland, and salt water enters rivers and groundwater. Yet even as shorelines advance across the continents, the total planetary inventory of water has begun its slow decline. This produces an apparent contradiction. Locally, there is too much sea. Globally, the planet is starting to lose it. The difference lies in timescale. Thermal expansion and melting reshape coastlines over centuries and millennia. Hydrogen escape reduces the planet's total water over much longer ages. Both processes arise from the same added energy, but they are visible in different ways. The first is measured by drowned land. The second is measured by molecules no longer bound to Earth. Feedbacks on land influence the oceans as well. Forest decline reduces rainfall recycling over continents. Stronger weathering carries dissolved minerals into the sea. Increased erosion delivers sediment and nutrients in intense pulses after storms and fires. Expanding deserts send dust across the oceans. sometimes fertilizing surface waters and sometimes changing cloud formation. Rivers may carry more water during brief floods, but less during long dry seasons. The balance between freshwater input and evaporation changes from basin to basin, altering salinity and currents. In the North Atlantic and around Antarctica, fresh meltwater can interfere with the formation of dense water that sinks into the deep ocean. If this overturning circulation weakens, heat and oxygen are redistributed, producing regional changes that can persist even while the planet as a whole continues warming. The sea is not merely a reservoir being heated from above. It is an active system whose currents determine where heat, salt, carbon, oxygen, and nutrients travel. As those currents adjust, some regions may warm rapidly, while others remain cooler for a time. Refuges for marine life can appear, then vanish as circulation shifts again. The approach to the moist greenhouse is therefore uneven. It advances through hot tropical air, weakening cold traps, altered clouds, and gradual hydrogen escape, while the deeper ocean responds on a slower clock. Even if the brighter sun were somehow dimmed after the transition began, recovery would not be simple. Lost hydrogen cannot easily be recalled. A warmer ocean stores heat for centuries. Collapsed ice sheets do not rapidly rebuild. Extinct ecosystems do not reassemble on command. The climate may cool, but the planet would return with less water and a different living world. This gives the threshold a one-way quality. Crossing it does not mean immediate destruction, but it changes what can be restored. Earth's oceans appear permanent because they have endured through ancient impacts, volcanic eras, ice ages, and shifting continents. Their persistence is real, but not guaranteed. They survive because the atmosphere, temperature, and solar energy have remained within a range that keeps most water cycling near the surface. A 10% brighter sun narrows that protection. The seas begin sending more vapor upward. The upper atmosphere becomes less dry, and hydrogen escapes into the dark beyond the planet. The ocean does not vanish in a great cloud of steam. It begins to leave in silence, one broken molecule at a time. Once water reaches the upper atmosphere, it enters a region where the familiar cycle of cloud, rain, river, and sea begins to break apart. Near the surface, water changes form but remains bound to Earth. It evaporates, condenses, freezes, melts, and returns. High above the weather, the same molecule faces stronger ultraviolet radiation and a thinner atmosphere. There, sunlight can split water into hydrogen and oxygen. The heavier oxygen remains more easily trapped, reacts with other substances, or joins the atmosphere. But hydrogen behaves differently. It is the lightest element, and some of its atoms can rise through the upper air until they reach heights where collisions are rare and gravity can no longer keep every particle confined. From that point, a fraction escapes into space. Under the present sun, this process is slow because very little water reaches the stratosphere. A cold layer near the top of the lower atmosphere condenses most rising vapor and sends it back down. Under a sun that is 10% brighter, the surface grows warmer, the lower atmosphere holds more moisture, and that cold barrier becomes less effective. More water enters the stratosphere, more molecules are broken apart, more hydrogen begins the long climb outward. The loss remains invisible from the ground. Yet it changes the future of the planet because escaped hydrogen does not naturally fall back as rain. The water cycle has gained a leak. At first, the leak is small compared with the size of the oceans. Earth holds an immense mass of water, and even a stronger escape flow would take an extraordinary span to remove it. This slowness can make the process seem harmless. A coastline may appear unchanged across many generations, while the upper atmosphere steadily carries away hydrogen. but geological change is often built from tiny rates acting without pause. Mountains rise through movements too slow to feel. Continents cross oceans at the pace of growing fingernails. In the same way, a planet can dry through losses that are negligible in a day and decisive across hundreds of millions of years. The key question is not whether hydrogen escapes at one moment, but whether the escape continues faster than water is supplied from the interior or delivered by rare impacts. Under sustained brighter sunlight, the outward flow gains the advantage. Ultraviolet radiation supplies the energy needed to break chemical bonds. Once a water molecule is split, hydrogen may appear as individual atoms or join into molecular hydrogen. These light particles diffuse upward through heavier gases. At the highest reaches of the atmosphere, temperature and radiation determine how many acquire enough speed to escape. Some leave through ordinary thermal motion. Others are accelerated by interactions with charged particles, sunlight, and the solar wind. Earth's magnetic field can influence the paths of charged particles, but it does not form a sealed shell around the atmosphere. Neutral hydrogen and particles moving along open magnetic pathways can still be lost. A stronger solar output may also heat and expand the upper atmosphere, increasing the region exposed to escape. The process is shaped by both climate below and space weather above. The warmer surface supplies more water vapor. Ultraviolet light breaks it apart. The upper atmosphere provides the route outward. Oxygen is left behind, but this does not mean the air necessarily becomes rich in breathable oxygen. The remaining oxygen is chemically active. It can oxidize surface rocks, react with volcanic gases, dissolve into oceans, and become bound in minerals. If life is declining at the same time, biological oxygen production also weakens. The final atmospheric composition depends on the balance among escape, geology, chemistry, and photosynthesis. On a lifeless or nearly lifeless world, oxygen left by water loss could accumulate under certain conditions, but it could also be consumed by the crust. A dry planet may therefore carry signs that resemble biology, while actually recording the destruction of its oceans. This possibility matters beyond Earth, because astronomers searching for life on distant planets often study atmospheric oxygen. Oxygen can be a biological clue, but a bright star and a history of water loss can produce it without living forests or oceans. Earth under a stronger sun becomes a lesson in how a potentially habitable world can create misleading traces as it leaves habitability behind. The escape of hydrogen also changes the chemistry of the upper atmosphere. Hydrogen participates in reactions that influence ozone, methane, and other compounds. As water vapor enters higher layers, those reactions become more active. The ozone layer, which absorbs much of the sun's harmful ultraviolet radiation, may be altered by changing temperatures and chemical cycles. A brighter sun does not simply add visible light and heat. It changes the radiation environment reaching the upper atmosphere, and atmospheric chemistry responds. If ozone declines in important regions, more ultraviolet radiation reaches the surface, increasing stress on organisms already facing heat, drought, and low carbon dioxide. Life in shallow water and on exposed land becomes more vulnerable. Organisms may retreat beneath soil, into deeper water, inside rocks, or under protective pigments and coverings. The drying of the planet therefore progresses together with a narrowing of safe environments. Earth's interior contains large quantities of water, bound within minerals rather than stored as liquid seas. Volcanism and tectonic activity can release some of it, while subduction carries surface water downward. Under modern conditions, these exchanges help maintain a broad long-term balance. As surface water declines and plate tectonics evolves, the balance may shift. Volcanic release can replenish local lakes, groundwater, and atmospheric vapor. but it is unlikely to match an increasingly efficient escape to space forever. The mantle becomes a reserve that delays complete drying rather than a source capable of restoring the ancient oceans. Water emerging from volcanic vents may fall as rain, collect in deep basins, or react with hot rock. Yet every molecule returned to the surface again enters the same warmer atmosphere and faces the same upward path. The loss of ocean volume changes climate in ways that can accelerate the decline. Smaller seas store less heat and provide less moisture to the atmosphere. Continents expand as shorelines retreat, creating wider interiors far from rainfall. Deserts grow across former seabeds. Salt and sediment are exposed to wind. Dust enters the air, altering clouds and reflecting some sunlight, but also darkening surviving ice and transporting minerals across the planet. Rain becomes concentrated near the remaining seas and high terrain. Rivers shorten. Lakes become temporary, appearing after rare storms and shrinking beneath intense evaporation. The atmosphere contains less total water once the oceans become greatly reduced. Yet the remaining warm basins can still feed a moist upper atmosphere. The planet may pass through a long transitional era in which surface water is scarce, but escape continues efficiently wherever heat and humidity overlap. Life follows the retreating water. Complex ecosystems disappear first because they require stable supplies, moderate temperature, and broad food webs. Microbial communities persist in aquifers, caves, porous rock, high-latitude refuges, and deep beneath the surface. Some use chemical energy rather than sunlight. These organisms are protected from ultraviolet radiation and rapid surface heating. But they still depend on water moving through cracks and minerals. As the hydrological cycle weakens, even underground habitats become isolated. Groundwater is no longer widely replenished. Hydrothermal systems continue where internal heat drives circulation, but they become scattered islands of habitability within a drying crust. The last biosphere may exist almost entirely out of sight, sustained by water released from minerals and energy from reactions between rock and fluid. Above it, the atmosphere grows thinner in water vapor overall, though the path of hydrogen escape remains open wherever water reaches high altitudes. There is no single day when Earth loses its oceans. The change is a sequence of thresholds. First, the upper atmosphere becomes wetter, then hydrogen escape increases. Later, ocean volume declines enough to reshape circulation and rainfall. Eventually, remaining water is confined to shrinking basins, deep rock, and temporary refuges. Each stage makes reversal more difficult. Even if the sun were dimmed after substantial loss, the missing hydrogen would not return. The planet could cool, but it would cool as a drier world. This irreversibility gives hydrogen escape its importance. Heat can leave through radiation. Carbon dioxide can move between air, ocean, and rock. Ice can melt and, under the right conditions, form again. Escaped hydrogen is different. It has crossed the final boundary. A 10% brighter sun therefore opens a slow route from the ocean to interplanetary space. The path begins with evaporation, passes through clouds and the stratosphere, continues through ultraviolet chemistry, and ends beyond the atmosphere. No wave marks the departure. No sound accompanies it. The sea is reduced by atoms departing one after another, carrying away the substance that once made the surface blue. Across immense time, the planet does not merely become warmer, it becomes lighter in water, and the darkness above quietly receives what Earth can no longer hold. As Earth grows hotter and drier beneath the brighter sun, life does not vanish in a single wave, it retreats. The first losses occur in the open, where complex organisms depend on stable temperatures. dependable water, breathable oxygen, and food webs made from many interlocking species. Forest animals decline as trees fail. Marine predators disappear as oxygen. Poor seas lose their productivity. Large bodies become difficult to cool. Long life cycles become liabilities, and specialized diets turn into traps when familiar prey or plants vanish. The biosphere begins to contract from continents, coastlines, and surface oceans toward places where heat arrives more slowly and water remains protected. For billions of years, organisms moved outward from sheltered water into sunlit seas, soils, forests, and air. Under the stronger sun, that movement runs backward. The most exposed and demanding forms disappear first, while smaller and simpler organisms persist in environments that once seemed marginal. Complex animals are especially vulnerable because their bodies require tightly controlled internal conditions. Heat pushes those systems toward failure. High humidity makes cooling by evaporation less effective. Lower oxygen increases the work required for every movement. Food scarcity forces animals to travel farther through landscapes that offer less shade and water. Reproduction becomes less reliable as embryos, eggs, and young animals face conditions adults can barely tolerate. Populations shrink, become isolated, and lose genetic diversity. A species may survive in scattered pockets, yet one drought, fire, disease, or failed breeding season can erase an entire refuge. Plants face a similar narrowing, though their retreat follows water, elevation, and carbon dioxide. Remaining forests gather near high latitudes, cloudy mountains, river corridors, and places supplied by deep groundwater. Grasslands persist longer where heat-tolerant species can use water efficiently. But even these communities weaken as carbon dioxide continues to fall. The landscapes between refuges become increasingly barren. Soil loses the roots that held it together, and rain runs quickly across hardened ground instead of soaking in. Each loss of vegetation makes the local climate harsher, reducing shade and moisture and raising surface temperature. The remaining habitats become islands separated not by ocean but by heat. Freshwater ecosystems collapse early because they depend on a continuous supply of rain, snowmelt, or groundwater. Rivers become seasonal. Lakes shrink into saline basins. Wetlands disappear except where underground water reaches the surface. Fish and amphibians lose connected habitats and cannot easily move between isolated pools. In the surviving water, evaporation concentrates salts and minerals. Organisms adapted to ordinary freshwater give way to species that tolerate brine, heat, and large swings in chemistry. A microbe does not need a forest, a river system, or a stable season. It needs only a tiny volume of liquid water, a usable source of energy, and chemistry that does not destroy its cells. In the oceans, the retreat follows depth and latitude. Tropical surface waters become too warm for many complex organisms and too strongly layered to receive nutrients from below. Cooler regions near the poles remain productive longer, especially where currents bring nutrients upward. Deep water offers protection from radiation and temperature extremes, but it contains less food as surface photosynthesis declines. Large marine animals disappear when the energy moving through the food web can no longer support them. Near hydrothermal vents, life draws energy from chemicals released by hot rock rather than directly from sunlight. Microbes use hydrogen, sulfur compounds, methane, and metals to build organic matter. Some vent animals may survive for a time through partnerships with these microbes. Yet even these ecosystems depend on ocean water circulating through the crust. As the oceans shrink and chemistry changes, the large vent communities eventually fade, leaving microbial films within cracks and pores. the surface becomes increasingly hostile to cells as ultraviolet radiation strengthens, temperatures rise, and liquid water becomes temporary. Life responds by moving beneath protective layers. A thin layer of soil can block damaging radiation, while deeper ground softens the cycle between day and night. Porous rock holds thin films of water long after the surface dries. Salt crystals can trap microscopic droplets. Caves preserve cooler air and collect moisture from condensation. Beneath deserts, ancient aquifers remain hidden from the heat above, though they are slowly depleted when rain no longer replaces them. These environments become the main continents of the late biosphere. Disconnected pockets of darkness where microbes continue reactions that began when Earth was young. Some survive by entering dormant states. Their metabolism slows almost to nothing, and protective molecules stabilize proteins and genetic material. They wait through long, dry periods, becoming active only when water returns. Dormancy extends survival, but it is not immortality. A refuge must occasionally provide enough energy and water for repair and reproduction. As wet intervals become rarer, the balance between waiting and living grows more difficult. Other microbes avoid dormancy by inhabiting the deep subsurface, where liquid water may persist in fractures far below the reach of sunlight. Cells may divide only after years, centuries, or longer, depending on the available energy. They feed on chemical reactions between water and rock, on hydrogen produced when radiation splits water molecules, or on organic material buried in ancient sediments. These organisms reveal that a biosphere does not require green continents or abundant oxygen. It can exist as a sparse network of cells scattered through stone. These refugees are not comfortable remnants of the old world. They're narrow chemical opportunities, sustained by cracks, minerals, pressure, and the faint movement of water. A slight change in temperature or flow can close them. Their endurance comes from low demand rather than abundance. By slowing growth and using reactions unavailable to surface organisms, microbes can remain active where almost no visible ecosystem could exist. The deep crust also offers protection from the changing atmosphere. Surface heat penetrates downward slowly, while geothermal warmth becomes more important than sunlight. Yet depth creates its own limits. Temperature rises below the surface, pressure increases, pores close, water becomes scarce, and chemical energy is consumed. Life is confined to a band between the overheated surface above and the hotter interior below. As solar warming drives heat deeper over time, that band narrows. The upper boundary moves downward, while the lower boundary remains set by the tolerance of cellular chemistry. Eventually, the habitable layer becomes a thin shell within the crust. High-latitude and high-altitude refuges may remain at the surface for a while, but they are temporary. As ice disappears and the atmosphere warms, the coolest climates shift toward the poles and mountain tops. Species follow until geography ends. When those last cool regions fail, surface complexity falls sharply. The survivors are organisms able to tolerate heat, salinity, acidity, dryness, or combinations of all four. Many are archaea and bacteria, forms of life without the complex internal compartments found in plants, animals, and fungi. Their simplicity allows flexible chemistry and survival in conditions that destroy larger cells. Some build protective communities called biofilms, layers of cells held within a moist matrix. A biofilm reduces water loss, traps nutrients, and allows different microbes to exchange chemical products. Together they create tiny ecosystems on mineral grains and fracture walls. The last life on Earth may not exist as isolated cells, but as these cooperative films hidden from the bright surface. Even microbial survival, however, depends on liquid water and usable gradients of energy. As the mantle releases small amounts of water, Local hydrothermal systems may continue beneath volcanic regions. Reactions between hot water and fresh rock create hydrogen and other compounds that microbes can use. These sites become rare oases, separated by enormous sterile regions. Each active fracture or warm spring extends the biosphere a little longer. Each failed system removes another island from the hidden map of life. The final decline is almost impossible to observe from above. The continents may already look empty. The oceans may be reduced to scattered basins. The atmosphere may carry dust across silent plains. Yet beneath a salt crust or deep within a warm fracture, cells continue to divide. Their existence is modest, but it preserves the continuity of life. Eventually, even these refuges become too hot, too dry, or too chemically exhausted. Water retreats deeper than cells can follow. Repair becomes impossible. The last active communities enter dormancy and fail to wake. Life ends not with a final visible creature, but with chemistry falling silent in a hidden pore. The brighter sun has not destroyed the biosphere in one act. It has pressed it inward, layer by layer, until the living earth survives only as a faint presence beneath stone. A brighter sun creates a problem unlike any ordinary climate crisis, because the source of the extra energy lies beyond Earth. Carbon can be removed from the air, forests can be restored, coastlines can be defended, and cities can be rebuilt. But none of these actions changes the star itself. If the sun remains 10% brighter, every generation inherits the same surplus of radiation. The only lasting response must either reduce how much sunlight reaches the planet, increase how much energy Earth reflects, move the planet into a different orbit, or transfer life somewhere else. Each possibility begins as speculation, yet each follows known physics. The question is not whether such interventions violate natural law. The question is whether intelligence, resources, stability, and time can grow large enough to use those laws on a planetary scale. The simplest idea is to make Earth more reflective. Bright clouds, pale surfaces, and reflective particles can send sunlight back into space before it becomes heat. In principle, increasing planetary reflectivity could offset part of the extrasolar brightness. High-altitude particles might scatter incoming light. Artificial aerosols could be released into the stratosphere, where they remain longer than particles near the surface. Large regions of rooftops, roads, deserts, or ocean could be altered to reflect more sunlight. These measures resemble natural events already known to cool the planet, such as major volcanic eruptions that fill the stratosphere with reflective material. Yet a temporary cooling effect is not the same as a permanent solution. Particles fall out, chemical reactions alter ozone, rainfall patterns shift. The atmosphere must be replenished again and again. If maintenance stops while the sun remains brighter, rapid warming returns to a world whose ecosystems and societies have adapted to artificial shade. A technological shield inside the atmosphere therefore creates dependence. It may buy time, but it must be sustained without interruption across centuries, millennia, and perhaps far longer. Clouds offer another route. Low marine clouds are bright and can reflect substantial sunlight. Fine sea salt particles released into the lower atmosphere might encourage the formation of more numerous, smaller droplets, making certain clouds more reflective. The method appears gentle because it uses ocean water in existing cloud systems, but its effects would still be uneven. Cooling one ocean basin could change winds and rainfall across distant continents. Monsoons might weaken. Storm tracks might shift. Some regions could benefit while others lose water. Any intervention large enough to counter a brighter sun becomes a global experiment whose consequences cross every border. A world already strained by heat would need cooperation stable enough to manage a machine affecting every climate and ecosystem. A more direct solution places the shield in space. A structure positioned between Earth and the Sun could block or redirect a fraction of the incoming light before it enters the atmosphere. The most discussed location lies near the point where the gravitational influences of Earth and the Sun allow an object to remain approximately aligned with both. A vast screen, cloud of small spacecraft, or swarm of thin reflective sheets could reduce the sunlight reaching Earth. To cancel a 10% increase, the system would need to intercept roughly 1 part in 11 of the brighter solar flow, though the exact amount would depend on Earth's reflectivity and climate response. The required structure would be immense, far beyond anything built in the present age, yet it would not need to be a solid disk. Millions or billions of lightweight elements could work together as a controlled swarm. Each element could adjust its orientation, letting the shade respond to changing climate conditions and fail gradually rather than without warning. Even so, the engineering challenge would be extreme. This swarm would need constant guidance because the balance point is not perfectly stable. Solar radiation would push on every thin surface. Collisions, material fatigue, micrometeoroids, and communication failures would accumulate. Manufacturing enough material on Earth and launching it into space would require enormous energy. A more advanced civilization might mine the moon, asteroids, or other bodies, avoiding the need to lift every component from Earth's gravity. In that case, the shield becomes not a single project, but an entire space-based industrial system. An entire industrial network would serve one purpose: preserving the climate of a distant blue world. Another possibility is to alter Earth's orbit. The amount of sunlight a planet receives falls with the square of its distance from the star. Moving Earth slightly farther outward could compensate for a brighter sun without continuously blocking light. To reduce received energy by about 1/10, Earth would need an orbital distance only several percent greater than its present one. That sounds small, but moving a planet is not. Earth carries an enormous mass and orbital momentum. No engine built on the surface could push it outward in any direct way. One conceivable method uses repeated gravitational encounters with asteroids or comets. A carefully guided body passing near Earth could transfer a tiny amount of orbital energy to the planet. Repeated across vast ages, such encounters might slowly expand Earth's orbit. The physics permits energy transfer, but the risk is severe. A navigation error involving a massive object near Earth could become an extinction event. The process would also disturb the Moon and possibly other planetary orbits. It would demand precision maintained over spans longer than civilizations have yet existed. Other versions might use beams, mass drivers, or solar sails to guide smaller bodies, but every approach requires coordination on an almost incomprehensible scale. These ideas reveal a central fact: moving a planet is theoretically simpler than changing a star, but practically harder than building almost anything else imaginable. The Moon may provide another tool. Its surface contains material that could be launched into carefully chosen orbits, creating a cloud that blocks some sunlight. Lunar dust is abundant and does not need to escape Earth's deep gravitational well, yet dust spreads, disperses, and responds strongly to radiation pressure. A poorly controlled cloud could interfere with satellites, dim the sky unevenly, or fall into the atmosphere. Long-term shading would require constant replenishment. Larger manufactured structures would be easier to control but harder to produce. The Moon could become an industrial base for a solar shield, joining Earth's climate system in a new way. If protecting Earth proves impossible, life might move outward instead. A brighter sun shifts the habitable zone away from the star. Mars receives more warmth. though its low mass and thin atmosphere make it poor at retaining liquid water. With advanced engineering, enclosed habitats could use its underground ice. Farther out, icy moons might become less hostile as sunlight increases, though their surfaces would still face radiation, low gravity, and unfamiliar chemistry. Artificial habitats could orbit the sun at distances chosen for comfortable temperatures. Unlike planets, these structures could control air, water, gravity, and light while moving outward as the sun brightened further. In that future, preserving life would no longer mean preserving one planet unchanged. It would mean carrying Earth's chemistry, organisms, and memory into a widening network of habitats. Yet migration does not remove the value of Earth. Its oceans, soils, atmosphere, magnetic field, and immense biological history cannot be recreated easily. A closed habitat may support descendants of terrestrial life, but it cannot contain the full complexity of a living planet. Protecting Earth therefore remains the richer goal, even if other refuges become necessary. The most realistic strategy may combine many approaches. Atmospheric reflection could provide short-term relief. A space-based shade could offer more precise control. Carbon management could limit additional greenhouse warming. Protected ecosystems, seed banks, underground habitats, and off-world settlements could preserve diversity against failure. Over longer spans, orbital engineering might gradually move Earth outward. No single device would save the planet forever. Survival would depend on layers of protection, each correcting the weaknesses of the others. The deeper uncertainty is not technological but social. Any system powerful enough to control planetary temperature can also distribute harm. It must be governed across regions with different climates, interests, and vulnerabilities. It must survive conflict, economic collapse, and changing cultures. It must be maintained by societies that may no longer resemble the ones that first built it. The brighter sun turns habitability into a responsibility carried across deep time. Physics leaves doors open, but it does not guarantee that intelligence walks through them. Earth may be protected, moved, shaded, or gradually abandoned. Each path remains possible only while knowledge, cooperation, and continuity endure. The star's growing light is slow enough to allow planning on a scale no natural disaster permits. Yet that same slowness demands a patience no civilization has yet demonstrated. The challenge is not merely to build a shield. It is to become a form of life capable of tending a world for ages. A brighter sun does not only transform Earth, it changes the map of possibility across the entire solar system. The habitable zone, the broad region around a star where liquid water may persist on a planet's surface under suitable atmospheric conditions, moves outward as stellar brightness increases. Earth begins near the inner part of that zone, and a 10% increase in solar output pushes it closer to the edge. Worlds farther from the sun receive more warmth, while those already near the inner boundary face growing instability. Habitability does not vanish from the system, it migrates. The shift is gradual, but its meaning is profound. A world once too cold may briefly become less hostile, while a world long rich in oceans may begin losing them. The same sunlight that narrows Earth's future can widen possibilities elsewhere. Mars becomes the most obvious candidate. It lies farther from the sun and presently receives much less solar energy than Earth. Its surface is cold. Its atmosphere is thin, and liquid water is unstable across most regions. A brighter sun raises temperatures and increases the energy reaching its polar caps. Shallow ice deposits and frozen ground. Seasonal melting could become more common in protected locations. Carbon dioxide frost would retreat, and buried water ice might thaw near the surface. For a time, the planet could appear closer to habitability than it does now. Yet warmth alone is not enough. Mars lacks the dense atmosphere needed to maintain stable surface pressure and strong heat retention. Liquid water exposed to the open air would still tend to freeze, evaporate, or boil away under low pressure. The planet's weak gravity allows atmospheric gases to escape over long spans. Added warmth may release water and carbon dioxide from ice and soil, but it may also accelerate their loss to space. Mars could experience a brief wetting without becoming a lasting ocean world. If intelligence were present, however, the brighter sun could make engineering easier, habitats would require less heating, solar power would be more abundant, greenhouse gases released deliberately into the atmosphere could have a stronger effect. Even then, transforming the entire planet would demand more than temperature. Atmospheric mass, radiation protection, soil chemistry, and long water retention would remain major obstacles. Mars might become more useful before it becomes truly habitable, serving as a refuge built through technology rather than a second natural Earth. Beyond Mars, the asteroid belt and outer moons also enter a slightly warmer era. The increase is not enough to turn distant ice worlds into open seas, but it changes surface temperatures, sublimation rates, and the stability of frozen compounds. On Ceres, water ice beneath the surface may become more mobile. The solar system's cold frontier remains cold, yet its chemistry becomes more active, farther out. The great moons of Jupiter and Saturn receive only a fraction of Earth's sunlight, so a 10% brighter sun does not suddenly melt their frozen crusts. Their internal oceans are controlled mainly by tidal heating, radioactive decay, and insulation beneath thick ice. Still, additional sunlight affects their surfaces and tenuous atmospheres. Titan's methane cycle may respond as its upper atmosphere receives stronger energy, though the moon remains extremely cold. These changes are modest compared with Earth's crisis, but they show that habitability depends on more than distance alone. A moon can hide liquid water beneath ice far beyond the classical habitable zone, while a planet inside that zone can become too hot for oceans. The zone is therefore not a sharp ring, but a shifting region of probability shaped by atmosphere, geology, clouds, rotation, and water inventory. Venus offers the clearest warning from the inner side. It already possesses a dense carbon dioxide atmosphere and surface conditions hostile to liquid water. A brighter sun only strengthens that separation from habitability. Its clouds may reflect much incoming light, but the atmosphere traps enormous heat. Any remaining hydrogen continues escaping from the upper atmosphere, preserving evidence of ancient water loss. Venus demonstrates that crossing the inner boundary can produce a state that remains stable for very long periods while being entirely unsuitable for complex surface life. Earth under stronger sunlight does not necessarily become a copy of Venus, because the two planets differ in atmospheric composition, water history, rotation, and geology. Yet the direction of risk is shared. As the habitable zone moves outward, Earth becomes less protected by its original position. The blue planet approaches a boundary that is not marked in space but expressed through water vapor, cloud behavior, and atmospheric escape. The movement of the habitable zone also changes how distant planetary systems are interpreted. A planet observed at one moment may appear comfortably placed around its star, but stars evolve. A young star can be dimmer, leaving planets frozen unless greenhouse gases compensate. An older star can brighten enough to drive the same planets toward water loss. Habitability is therefore a chapter in time, not a permanent label. A world may pass through a long temperate interval and then leave it. Another may remain frozen for ages before briefly warming. Life, if it emerges, must fit within that moving window. The 10% brighter sun makes this temporal nature visible within the solar system. Earth's favourable conditions are not a fixed gift. They are part of an evolving relationship between a star and a planet. The length of that relationship depends on feedbacks. Carbon dioxide weathering can extend habitability by reducing greenhouse warming. Clouds can reflect more sunlight and delay heating. Ice loss can accelerate the approach to the inner edge. Tectonics can recycle carbon, while biology can reshape atmospheric chemistry. These systems have helped Earth remain inhabited despite the sun's gradual brightening across deep time. Yet every stabilizing process has limits. Weathering can remove so much carbon dioxide that plants fail. Reflective clouds may change with circulation. Oceans can become a source of greenhouse vapor. The habitable zone defined only by orbital distance cannot capture these internal struggles. Two planets receiving the same sunlight may follow very different paths because one has deep oceans and active geology, while the other has thin air and dry rock. If Earth could be moved outward, its position within the habitable zone might be restored. A slightly wider orbit would reduce the solar energy reaching the surface and could preserve liquid water, in theory. Carefully controlled gravitational encounters or other vast engineering methods might transfer orbital energy to the planet. In practice, such a project would unfold across immense time and require precision beyond any current capability. Yet the idea reveals something important. The danger does not come from brightness alone, but from brightness at a particular distance. Changing either side of that relationship could preserve the balance. If Earth remains where it is, then future life may have to follow the habitable zone outward through settlements, artificial worlds, or migration between planets and moons. Such movement would not resemble a single departure. It would be a long dispersal. Habitats might first appear in orbit, then near the Moon, Mars, and the asteroid belt. Closed ecosystems would carry water, microbes, plants, and stored genetic diversity. Over time, civilization could spread into regions where the brighter sun provides useful energy without overwhelming heat. Artificial habitats would allow distance, shielding, atmosphere, and temperature to be chosen rather than inherited. In that sense, the habitable zone could become something designed. Life would no longer depend entirely on the natural surface of one planet. Yet even a vast network of habitats would not replace Earth's depth of complexity. A planet contains countless chemical cycles, hidden microbial communities, weather systems, and evolutionary relationships that cannot be fully copied. Migration may preserve descendants, but preservation of the whole biosphere remains far more difficult. The outward movement of habitability therefore carries both promise and loss. Mars may warm, icy worlds may become easier to use, solar energy may support distant settlements. At the same time, Earth's oceans thin, its forests retreat, and its atmosphere changes beyond recognition. The solar system gains no true replacement for the living world it loses. It only offers new locations where fragments may continue. A 10% brighter sun turns the idea of a habitable zone from a quiet astronomical diagram into a moving frontier. The inner worlds become harsher, the colder worlds become slightly less remote, and the region suitable for liquid water slides away from Earth's orbit. Across that shifting map, habitability appears not as a permanent place but as a passing alignment among light, air, rock, and water. Earth occupies that alignment for an extraordinary span, but not forever. The star continues shining, the zone continues moving, and life faces the final question of whether it can move with it.